All right, let's talk about that feeling. You're staring at a physics problem, maybe one from a book like Irodov, and your brain just goes blank. We've all been there. Well, today we're going to face one of those classic problems head on, problem 1.114. We are going to conquer it together, step by step. If the whole idea of non-inertial or rotating reference frames makes your head spin a little, you are in good company. It's honestly one of the trickiest concepts in classical mechanics. But don't you worry, we're going to untangle this whole thing and make it make sense. And this is where our challenge comes from, i.e. Irodov's Problems in General Physics. For generations of physics students, this book is a rite of passage. The problems in here are designed to do more than just test you. They're made to build a deep, unshakable intuition for the laws of nature. They are tough, for sure, but they are incredibly rewarding. And our specific mission today is problem 1.114. I love this problem because it brilliantly weaves together a bunch of key ideas about what happens when things move in a rotating world. Okay, so before we even think about writing down an equation, what's the first rule of problem solving? You've got to understand what you're up against. So let's deconstruct the problem statement, piece by piece, and see what it's really telling us. Right off the bat, Irodov throws us a curveball. We have a disk spinning at a constant rate omega, but look where the axis is. It's not through the center, it's passing through its edge. This is so important. So instead of a record spinning on a turntable, picture a frisbee with a nail through its rim spinning around that nail. It's a totally different motion. And here's the next huge clue. There's a particle, mass m, moving along the rim. But notice the wording. Its velocity is constant relative to the disk. That phrase, relative to the disk, is a giant flashing neon sign. It's telling us we need to put ourselves on that spinning disk and see the world from its point of view, a non-inertial reference frame. And here it is, the golden ticket, the one condition that unlocks the first part of the puzzle. At a very specific instant, when our particle is as far as it can possibly get from that pivot on the edge, the inertial forces acting on it completely cancel out. They add up to zero. This is our starting point for part A. But what on earth are inertial forces? So, to handle this, we need to open our conceptual toolkit. Inertial forces aren't real forces in the way gravity or a push from your hand is real. Think of them more like correction factors. They're mathematical tricks we have to use to make Newton's good old laws like F equals ma work correctly when our viewpoint is spinning or accelerating. Let's break it down. An inertial frame is just a fancy way of saying a viewpoint that's not accelerating. Maybe it's moving at a constant velocity, or maybe it's still. Here, Newton's laws work perfectly. A non-inertial frame, like our spinning disk, is accelerating. And to use Newton's laws here, we have to introduce these extra fictitious or inertial forces. The first one is a force you've definitely felt, the centripetal force. You're on a merry-go-round and you feel like you're being flung outwards, right? That feeling is what we call the centripetal force. It's not a real thing pulling you. It's just your body's inertia trying to go in a straight line while the ride keeps turning you. Now, the second one is a bit weirder, the Coriolis force. This is an apparent force that only pops up for objects that are moving inside the rotating frame. It's a deflecting force. This is the guy responsible for the spin of hurricanes, and it's the force that's going to be so important for our particle moving along the rim of the disk. Okay, deep breaths. This is the master equation that governs motion in a rotating frame. It looks like a monster, I know, but it's our best friend here. Let's translate it. The left side, m times w prime, is just F equals ma, as seen from the spinning disk. W prime is the acceleration relative to the disk. On the right, F is for any real forces. Then we have our two new friends. The middle term is the centrifugal force, and that last term with the cross product is the Coriolis force. The problem tells us that these last two, the inertial forces, are the ones that add up to zero. All right, theory's done. Let's get our hands dirty and actually solve part A. We're zooming in on that one special moment when the total inertial force is zero, and our goal is to find the particle's acceleration, w prime, relative to the disk. First things first, let's draw a map. We'll place our origin, our 0, point, right on that pivot on the disk's edge. Now, where's the particle? The problem says it's at its maximum distance from that pivot. A little bit of geometry tells you that's got to be on the complete opposite side of the disk, a full diameter away. So its position vector r has a length of 2r. Now let's think about directions. The angular velocity vector omega points straight up. The particle's relative velocity, v prime, is tangent to the rim right at that point. And now we use our secret weapon from the problem statement. The total inertial force is 0. That means the centrifugal force, which is trying to fling the particle away from the pivot, is in a perfect tug of war with the Coriolis force. And at this one moment, it's a perfect draw. They balance completely. And this is the whole trick to solving part A. At this specific point, the centripetal force points straight outward from the pivot. And if you work out the cross product for the Coriolis force, you find it points straight inward, along the exact same line. They are perfectly anti-parallel. The only way two vectors pointing in opposite directions can add up to 0 is if their lengths, their magnitudes, are exactly the same. This turns a messy vector problem into simple algebra. So let's do it. We just set their magnitudes equal. The centrifugal force is m omega squared times the distance, which is 2r. The Coriolis force is 2m omega times the relative speed, v prime. We put them on either side of an equal sign, the m's cancel, one of the omegas cancels, and we find that v prime is just omega times r. Simple. But we need the acceleration, w prime. Well, for any object moving in a circle, its acceleration is just its speed squared divided by the radius. In our case, that's v prime squared over r. We plug in the v prime we just found, do a little algebra, and voila! The relative acceleration, w prime, is omega squared times r. That's our answer for part A. Nice. Part A is in the bag. But of course, Irodov isn't going to let us off that easily. For part B, we have to zoom out. We need to find a general formula for the net inertial force at any arbitrary position, not just at that one special point. So, our new goal is to create a general rule. We want an expression for the total inertial force, Fn, that works no matter where the particle is along its path, for any distance r from the pivot. So how do we tackle this? We can't just set the magnitudes equal anymore, because now the forces aren't always pointing in opposite directions. The centrifugal force always points radially out from the pivot, but the Coriolis force is always directed toward the center of the disk. This means the angle between these two force vectors is constantly changing as the particle moves. And what do we do when we need to add two vectors that aren't lined up? Yep, we've got to use vector addition, which in this case means using the good old law of cosines. So you grind through the vector addition, you do a little bit of trigonometry based on the geometry of the disk, and out pops this, admittedly kind of wild-looking formula. But check this out, this is the cool part. Let's test it. What happens if you plug in r equals 2r, which was our special case from part A? Well, that 2r over r term becomes 1. 1 squared is 1. 1 minus 1 is 0. The square root of 0 is 0, and the whole force becomes 0. It perfectly matches our result from part A. This formula works. Phew, we did it. We wrestled with an Irodov problem and we came out on top. But, just getting the answer isn't the real prize. The real win is understanding the concepts and knowing what traps to avoid next time you see a problem like this. So let's make a quick survival guide. These are the most common pitfalls. Number 1, always be clear which frame you're working in. Are you on the ground or are you on the spinning disk? Number 2, that little factor of 2 in the Coriolis force. It is the most forgotten number in all of mechanics, I swear. Don't forget it. 3, vector directions are everything. Use your right-hand rule for cross products and be careful. 4, don't mix up relative velocity with what an observer on the ground sees. And finally, number 5, don't jump straight to magnitudes. Start with vectors, get your directions right, and then simplify. It'll save you so much trouble. Okay, so I want to leave you with one final question to chew on. Back in part A, at that one magic moment, the inertial forces, the fictitious forces, canceled out. They vanished. So does that mean our little particle feels no force at all? Is it just coasting? Think about it. There must be some real forces acting on it to keep it moving in a circle, right? So what are they? What is actually pushing or pulling on that particle? That's something to ponder.